Understanding host interconnect congestion. So Saksham will be presenting, and Saksham Agrawal is a PhD student at Cornell University. His research is broadly related to network design for data centers. He'll talk about a newfound problem of host congestion, which recently started to occur with the introduction of high-speed networks. So today he'll be presenting Understanding Host Intercongestion. Internet. Go ahead.
Yeah, thanks, Hakeem. All right, congestion. Let's talk about congestion. So when we think about congestion, the first thing that comes to our mind is network switches and switch buffers. But this project started with a surprising new observation. Our measurement infrastructure told us there is congestion happening somewhere along some path and packets are being dropped. But we did not see any triggers for switch buffer overflows. So we spent quite some time trying to understand this problem. And today I'm going to share with you what we have learned so far. All right, let's jump right in. So the conventional wisdom in the community has always been congestion happens inside the network core. This can be due to multiple possible reasons, including oversubscription, incast, poor load balancing, etc. And there has been decades of work in trying to build deep understanding of this in-network congestion problem. We know good reasons for this kind of congestion. We have developed understanding of good congestion signals and response. However, today, I'm going to talk about this new problem of host congestion. I'm going to give more details in a minute, but at a very high level, what's happening here is that with the introduction of these 100G, 200G links, new bottlenecks have started to emerge in the host interconnect. That is the data path between NIC to the CPU or memory. So this is a bit surprising because typically the host interconnect is assumed to have much larger bandwidth than the typical NIC line rates. So in this talk, I'm going to talk about this problem of host congestion, what it is, what are the root causes of this problem, and then how can we rethink our congestion control and host architecture in order to resolve this problem. Okay, but before we try to understand the host interconnect congestion problem, we need to understand the host interconnect first. So I'm going to give you a very brief primer of the host interconnect architecture today. I'm going to give details of Intel specific architecture for this talk, but the broader ideas carry over to other architectures as well. All right, so here's the host. There's a NIC. We have CPU cores. And then there's DRAM. Now, CPU cores talk to each other using this thing called a processor interconnect. And then they talk to the DRAM using these channels called memory channels. And the NIC talks to the CPU or the memory using this thing called a PCI interconnect. There's also this module called the IIO, Integrated IO Controller, whose main job is to intercept these PCI requests and then convert them into memory read or write requests. Now, there are two important aspects of this host interconnect. First, it is lossless. So it uses a credit-based hop-by-hop flow control mechanism. Just to give a rough idea, what happens is, suppose a NIC received a packet, it wants to DMA to the memory. First, it uses PCIe using some fixed number of credits. And then these credits are released once the packet lands into the DRAM. All right. A second interesting aspect of this host interconnect is that it's shared. So both the compute and the PCI traffic can use this shared interconnect. For example, you can see the memory channels are used by both the CPU and the PCI traffic. All right, so now we have a better understanding of the host interconnect architecture. Let's understand the host congestion problem. So normally what happens, your NIC receives packets at say line rate and your interconnect is fast enough to drain them promptly. But what happens in host congestion scenarios is that your PCI bandwidth starts to get underutilized for some reason. Now, intuitively, intuitively, the formula for any lossless interconnect utilization is given here. So what it essentially tells you is that if the latency for any PCI request inflates a little bit, your inherent parallelization, which is provided to you by the number of credits, it can help you offset that increase in latency. But then there comes a point when you finally run out of credits, and then you enter this host congestion regime. And then your PCI bandwidth starts to get more and more underutilized. And it is then the NIC is unable to drain the packets at the rate at which they're arriving. You start seeing queue buildup and eventually packet drops. So let me give you some very quick evidence of host congestion happening in Google's large-scale production clusters. So these clusters were running Snap with Swift as the congestion control protocol. Now, Swift is known to provide you minimal limit for congestion, and Snap already provides the auto-scaling mechanisms for increasing CPU cores if there are CPU bottlenecks. Yet, we saw lots of packet drops happening at the end hosts. Now, here I show you the host packet drop rates with increasing link bandwidth utilization. There are two interesting takeaways here. One, we see increasing host drop rates with increasing link bandwidth utilization. And second, and perhaps even more surprising, we see significant drop rates even when the link bandwidth was like far from saturation. Now, I'm going to dive into the root causes of this problem in a minute, but let me just quickly note that we can see significant impact on app level performance because of host congestion. For instance, we can land into poor isolation because of host drops. We can see inflation in tail latencies, lower application level throughput, and so on. All right, so now we have understood the problem. Let's try to understand the root cause. What is it that was increasing this PCI request latency, which was reducing my PCI utilization and causing the host congestion problem? All right, so there are multiple bottlenecks which are emerging in our host interconnect architecture, which are inflating this PCI request latency. One of them is the shared memory channels used by both the CPU traffic and the NIC traffic. So now in terms of resource balancing, the memory bus used by today's servers has always been oversubscribed. So to give you an example, on state-of-the-art Intel servers, you can see that you can saturate the memory bandwidth only using around 6 CPU cores. But normally, you still do not see your memory always saturated because you normally do not use all your CPU cores reading or writing to memory at the same time. However, this equation started to change when we added more and more and more NIC bandwidth and increasing PCI bandwidth. So now what started to happen is that your memory bus started to run much more closer to saturation much more often. And just like any closed loop system, when you put more and more load on the system, you start seeing more and more latency. So essentially your IIO to DRAM latency started to increase, thus also increasing the total PCI request latency and causing the host congestion problem. Now this problem is only poised to get worse because my DRAM bandwidth per core has remained relatively stagnant over time, but my NIC bandwidth or my PCI bandwidth has been increasing much more rapidly. Now let's look at another bottleneck, which is a slightly more complex. It stems from the need for providing memory protection against the IO devices. So today's NICs are only equipped with virtual memory addresses to provide this memory protection. And the IIO therefore needs the physical address to actually transfer the packets to the memory. So the IIO consists of this device called the IOMMU, whose main job is to perform these translations, and it does that using some IO page table, which sits in the DRAM. And to speed up these translations, IOMMU also contains a cache called the IOTLB. Now the problem arises when you see an IOTLB miss. Whenever you see an IOTLB miss, then for each PCI request to perform the translation, you might need to do an entire page table walk, which might result in one or multiple memory accesses, leading to increasing PCI request latencies. Now, even this problem is also poised to get worse because we are rapidly increasing our NIC bandwidths, and that causes our BDP to also increase correspondingly. And that causes the number of active IMMU pages that you're going to use correspondingly. But on the same time, the IOTLB sizes have remained relatively stagnant, causing more and more IOTLB miss rate. So our paper provides more details of the workloads which can be used to create host congestion scenarios. And we also provide some surprising new observations, which we found running the existing congestion control protocols in the host congestion regime. And note that all these results are also reproducible even on commodity clusters running Linux, and feel free to reach out to me if you need more help representing those. All right. So now let's try to think about what are the future directions that host congestion problem embarks us upon. So we spent quite some time last year trying to investigate this problem, to understand what was actually going on. This process was super exciting. But I believe what is even more exciting is to how to think about solving this problem. Now, there is one longer term direction that we need to rethink the host architectures so that we do not encounter this problem in the future. So there are some upcoming hardware trends. Like, for example, we have these PCI enhancements which are proposed, like CXL, which can provide us memory coherent channels and can help reduce PCI latency. So it might be good in the short term, but in the longer term, we might still run into the similar bottlenecks like I discussed before. We might also think about other interesting directions, like using better memory protection mechanisms or better memory bandwidth sharing mechanisms in order to solve this problem. This whole line of host congestion has also led us to rethink how we do this classical congestion control. So the traditional congestion signals like ECN, drops, or delays might not bode well with the host congestion problem. I think for host congestion, we would need to look for new congestion signals, like from outside the network stack. For example, what is the memory bus utilization? What is the number of active IMEI pages you're using? And not just in terms of new congestion signals, we also need to rethink how we respond to those signals. Ideally, we would want to have different kinds of responses for different root causes of the host congestion problem, right? And also we need to rethink the time scale of our responses, because the degree of host congestion can change much more rapidly, even at microsecond or sub-microsecond level. We might even need to think about sub-RTT responses for the future congestion control protocols. Right, to summarize, today I talked about this newfound problem of host congestion, which has started to emerge because of new bottlenecks emerging in the host interconnect hardware. I told you what is the host congestion problem, what are its main root causes, and what can we do to think about solving this problem in the future. Thank you.
Hi, this is Wei Tao. I really agree with your vision, and I think one of the problems you said is the cache behavior is somewhat unpredictable. So, do you have anything like you have a vision, but that vision cannot predict cache behavior also, right? So how do you solve this problem? You think maybe?
Can you please clarify a little bit what do you mean by cache behavior?
Yeah, okay. Yeah, I'm too excited. Okay. So I think one of the root causes of this host congestion problem is cache behavior is somewhat unpredictable, depending on your traffic load or traffic pattern, right? So how do you think you can resolve this cache behavior problem with your new vision?
I'm still a bit unclear what you mean by cache behavior.
I mean, some traffic load or traffic pattern will lead to cache miss. So that problem, do you think it can be resolved?
I see. Okay.
Yeah.
Right. So you're right. So for example, if I talk about the IMEI contention problem, and if I want to think about how would I ideally want to reduce my IoT-LB miss rates, one way could be like if I could somehow reduce the number of active IMEI pages which are being used. So one way I imagine it could happen is like if there was some mechanism where you could limit the number of active flows or active connections at any point of time in the network. So that would inherently cause you to reduce the number of active buffers at any point of time being used, and could reduce your cache miss rates and maybe reduce this congestion problem because of the IMMU bottleneck.
I see. Very cool. Thank you.
And then actually just one more question, and then we'll have to take the rest of the panel.
Hi, Saksham. Srinivas here from Rutgers University. Cool talk. I think I'm missing something basic. If you could clarify it, that would be great. So on a server, the memory bandwidths that are advertised today, like on a Haswell architecture, is like 50 to 100 gigabytes per second. So that's actually much higher than the NIC bandwidth that we have. So why is there memory bandwidth contention? Like what's happening?
Yeah, so you're right. So we can have like 50 to 100 gigabytes per second per socket bandwidth. But if you look at like high-speed links today, for example, if you have 100 Gbps or 200 Gbps NICs, so 100 Gbps is already around 12.5 gigabytes per second of memory. And with 200, you already get like 25 gigabytes per second, which is already around 50% of the memory capacity you say. And a single CPU core itself uses around 20 gigabytes per second bandwidth. So it's very unlikely that you'll be using only network traffic at any point of time. But even if you're using like 2 or 3 or 4 CPU cores, along with the memory traffic, which is very likely, and we observe it in production, you start seeing this problem.
It's a per core limitation plus the access that the core itself does to memory outside of networking.
Right.
That's kind of, okay. Thanks.
Great, let's begin. So for our next talk, I'd like to introduce Ray Pan. Ray is a first-year PhD student at Princeton University, advised by Ravi Utrali. Prior to joining Princeton, he received his bachelor's from University of Wisconsin, and he did an internship at Max Planck in Germany, where he did this work. So today he's going to present efficient flow scheduling and distributed deep learning training with echelon formation.
I have to understand what he meant by
Thanks, Akin, for the introduction. My name is Ray, and today I'm happy to present our work. Oh, sorry. Thanks. Back to what I was saying. Today, I'm happy to present our work on performing efficient flow scheduling in distributed deep learning training with echelon formation. I did this project during my internship at the Max Planck Institute for Informatics. So deep neural networks have evolved rapidly in the recent years. Models like ResNet, BERT, and GPT-3 have empowered state-of-the-art results across a wide range of applications. Before we deploy these DNNs in applications, however, they first need to be trained. So nowadays, training is usually done in a distributed manner in a cluster, where the workers use the network for communicating model weights and intermediate data. A trend in the recent years is that both the models and the data sets are getting bigger. And as a result, communication is increasingly becoming a bottleneck in distributed training. For example, in prior work, people have found that as much as 80% of the overall time is spent on communications. Therefore, improving the communication efficiency in distributed training is crucial to minimizing the iteration time. So flow scheduling is a great, powerful tool to alleviate the communication bottleneck. It reduces the flow completion times and ultimately the overall completion time as well. CoFlow is the most relevant network abstraction for data parallel applications to express their performance goals. It defines a group of semantically related flows that are optimized to finish at the same time. In the example of a MapReduce job, we can say that all flows in the shuffle stage constitute a CoFlow, and the CoFlow will not finish until all its flows finish. Now, CoFlow is a really good fit for some of the traditional big data frameworks, but unfortunately, it doesn't work too well for some of the modern machine learning training paradigms. The reason why flow scheduling doesn't apply to machine learning is because you don't need to read all of this. They're having a bunch of different parallelization strategies for distributed training, and they have drastically different communication patterns, which makes it really difficult to come up with a network abstraction that unites them all. Next, let's look at a concrete example of how existing network abstractions fail for machine learning. So the training paradigm we're showing here is called pipeline parallelism, which is a form of model parallelism. In this paradigm, each neural network is partitioned across multiple workers that each includes consecutive layers of the neural network. And each input data sample is passed through the workers sequentially. In this example, we have 4 workers. To maximize the training efficiency, each training mini batch is further split into multiple micro batches so that the training can be done in a pipeline. shown in this figure where we have 3 micro batches, each labeled with a number. And each iteration includes a forward phase and a backward phase. Note that this figure on the right only plots the computations and omits the communications for simplicity. So if we are to zoom in on the first 2 workers during a forward pass and plot the computation communication dependency graph, we have something like this, where each square block denotes a forward compute. Each yellow circle denotes a network flow that carries the intermediate data, and each arrow denotes a start-after dependency. So the problem with modeling these flows is that the communication patterns in distributed training are more sophisticated than those in traditional big data applications, and the flows may not finish at the same time. In the example of pipeline parallelism, the computations form a staggered manner, so the flows should similarly finish in a staggered manner. So suppose the interworker network bandwidth is B, and each network flow carries 2 B units of data. If we are to use co-flow scheduling naively, it will make all flows finish at the same time. And it takes 10 seconds to finish this training phase, which is even worse than fair bandwidth sharing. In the optimal case, we would maintain the staggered shape of the pipeline to obtain an ideal computation communication pattern and maximize the training efficiency. So in this case, the optimal is able to reduce the iteration time. And we do this optimal case with our network abstraction, echelon flow. The insight of our echelon flow abstraction is that the finish times of flows in distributed training should follow the computation patterns in distributed training, as communication is there to facilitate the upcoming computation. We find this nature similar to echelon, a military terminology that describes the formation of units like planes or troops. So an echelon formation is defined by the shape and distance between units. Similar to military units, we find that computation units in distributed training also form specific patterns, where the shape is predetermined by the training framework that we know ahead of time. And the distance is just the computation time on each worker, which can be profiled. For data transmission between workers, we define the ideal finish time as the earliest possible time that a flow can finish, which is usually the start time of the flow, like this. By minimizing the flow completion times with regard to the ideal finish times, we can make the flows finish as fast as possible, maintain the ideal computation communication pattern throughout the training process, and maximize the training efficiency. Now, in case flows are delayed due to unexpected conditions like congestions in the network, we set the ideal finish times more aggressively so that the upcoming flows can receive more bandwidth allocation, catch up, and reduce the deviation from the ideal computation communication pattern. Formally, we define an echelon flow as a set of flows with related ideal finish times that are not necessarily equal, but their relationship can be represented by an arrangement function that describes how the flows should be arranged to maintain the ideal computation communication pattern. Echelon flow is pretty expressive in the sense that it is capable of modeling training paradigms that cannot be modeled with CoFlow. But for brevity, we're only going to look at pipeline parallelism. Please see our paper for more details on how we use echelon flow to model other training paradigms. So here is how we use echelon flow to describe pipeline parallelism. Instead of using CoFlow to say, hey, these flows should finish at the same time, our abstraction tells the network when the first flow in the echelon flow will finish, and the distances between flows in this echelon flow. In pipeline parallelism, the distance t is simply the computation time of one forward pass of one microbatch on one worker, which can be profiled. As a quick recap, echelon flow is a generic network abstraction for a diverse set of distributed training paradigms. It is a superset of CoFlow, which entails that existing CoFlow scheduling algorithms can be extended to echelon flow scheduling fairly easily, and they have the same complexity. So a natural question to ask is, how is flow scheduling for machine learning possible? Our abstraction assumes prior knowledge on the flow size, computation time, and computation communication dependencies, because deep learning training is a highly iterative process, and is predictable in the sense that the GPU computation time can be profiled, and the flow size and dependencies are fixed across iterations. Therefore, in an actual system, we can use profiling to obtain this information required to formulate an echelon flow a priori. Please see our paper for a more detailed sketch of our envisioned system. So to conclude, echelon flow is a generic network abstraction for diverse distributed training paradigms. Key to it is an arrangement function that describes the flow finish patterns for higher training efficiency. Through this paper, we hope to encourage the community to do a better job at integrating machine learning systems and network management so that we can manage the networks more proactively instead of reactively. Thank you for listening to my talk, and I'm happy to take questions.
Hi, this is Henry from Berkeley from Princeton University. I was just curious, particularly in the pipeline parallelism case, really alone, would it work to just have a first in, first out sort of scheduling algorithm? Because it seems like you just need that first flow to go through before the second one can.
That is a great question and a very acute observation. So the thing with pipeline parallelism is that in specific training paradigms, we do have some heuristics that achieves the optimal. But these heuristics are not really generalizable to all training paradigms. Like there has been a bunch of prior work on not using FIFO for different paradigms like data parallel. And in case like these, if we are actually using these heuristics, our abstraction is still able to self-correct in case of unexpected network delays.
That makes
With
sense.
that.
Thank you.
Hello, I'm Taranum from UT Austin. So like here you are talking about like there are different kind of pipeline parallelism possible. So does your like model take care of all of them because they have like different network patterns?
That's a great question. So there are multiple implementations of the same training paradigm. Like, so in this paper, we're only focusing on the gpipe implementation because it's the simplest one to describe. And if we are to model different implementations like PipeDream, we would need some more complicated arrangement functions that we're not showing here. But yeah, I think as long as we can know those dependencies a priori and we have fixed GPU computation times, then our abstraction is able to describe all those paradigms.
Thank you.
Okay, let's thank the speaker again. And then next up is Sudarshan. He is a PhD student at MIT working with Manya. He loves working on problems related to distributed machine learning, congestion control, resource allocation, and packing. He is looking for a summer internship. So if you're at a company or what and have some ability to hire interns, so please take a close look and follow up with him. And today he's presenting congestion control and machine learning clusters.
Thank you so much for the introduction. Hi, everyone. I'm Sudarshan. This talk is about congestion control in machine learning clusters, and specifically, why TCP fairness is not necessarily beneficial in ML clusters. With the rise of machine learning in the modern life, machine learning training is becoming a dominating workload in today's data centers. So there is a significant need to efficiently train large deep neural network models. But today's ML clusters tend to ignore the impact of congestion control algorithms when two or more jobs share a network link. For instance, state-of-the-art ML scheduling algorithms try to place workers based on topological proximity. That is, workers of the same job are placed as close as possible so as to avoid the chances of congestion. But even with careful job placements, network contention is inevitable when the cluster is really large. Let's take an example. We have a small cluster with 12 servers. Say there are 2 training jobs, each taking up 6 servers. In training job 1, server 4 has to communicate with server 5 and uses the link L1. Similarly, for job 2, server 8 and 9 have to communicate and are forced to share link L1. This shows that even in such a small cluster, placing jobs based on topological proximity, still we end up having congestion. So this brings up the question, what is the impact of congestion control algorithms when two or more jobs share a network link? In this talk, I'm going to show you that fair congestion control protocols are not necessarily beneficial in ML clusters. In fact, adding some amount of unfairness actually helps improve the training performance for all the jobs in the combination. Let's take a simple example. We have one DNN model and we use two servers to train it. The servers are connected using 50 Gbps links and they use RDMA congestion control. If I plot the link utilization, we see that the training starts with the compute period where there is no network demand. Let's call this as the compute phase. This is followed by a region of heavy network demand. This is known as the communication phase. Together, they form one training iteration. Typically, DNN models have to be trained for several thousands of such iterations. This shows that DNN training has a periodic on-off traffic pattern. Now I'm going to show you something unexpected. We have job 1, which uses server 1 and 2. Let me add another DNN model, which uses server 3 and 4 and shares the middle link. Firstly, let's test the default congestion control protocol, DCQCN. DCQCN is a fair congestion control protocol. So when we plot the link utilization, we see that both the jobs get 50% of the link bandwidth. Nothing surprising here yet. Let me do a thought experiment. We run the same experiment, but now I'm going to change the DCQCN parameters of job 1 such that the link sharing is now 60-40 instead of 50-50. Now, when I plot the link utilization, we see that job 1 gets 60% of the bandwidth when both of them try to use the network. Let me ask a question here. Say if I run both the scenarios for a long time, which job among the 4 do you think will have the fastest iteration times? Intuitively, I'd assume that since job 1 is getting more bandwidth, it should have the fastest iteration times in the unfair bandwidth sharing case. And job 2 of the unfair bandwidth sharing case should have the slowest iteration times. But when I run the experiment for 1,000 iterations and plot the CDF of the iteration times, what I see here is both job 1 and 2 of the unfair bandwidth sharing case have almost similar iteration times. In fact, what is more surprising is that they have faster iteration times as compared to the fair bandwidth sharing case. Isn't this surprising? Just adding some amount of unfairness helps in making the training time much faster as compared to the fair bandwidth sharing case. Let's dive deeper and see what's happening here. Let me plot the link utilization for a few more iterations. For the fair bandwidth sharing case, the following iterations are similar as for the first iteration, where both the jobs try to communicate together and get half the link bandwidth. Let's look at the unfair bandwidth sharing. As we saw before, in the first iteration, job 1 gets 60% of the link bandwidth and is able to complete its first iteration faster. Job 2 gets less bandwidth and it takes a little bit longer to complete. In the second iteration, since job 1 was able to complete its first iteration faster, it starts its communication a little earlier and is now able to utilize the full network for a short while. Now, job 2 also starts communicating and they both share the network unfairly. In the third iteration, this effect is becoming more prominent. Job 1 is able to start even earlier and is able to utilize the full network for a longer duration. And if we see from first to third iterations, we see that the region where both communicate together progressively reduces. If we let it run for a few more iterations, we see that unfairness completely separates the two communication phases of the two jobs. This interleaving of communication phases actually helps both the jobs to utilize the full network bandwidth. And this is the reason why unfairness had better iteration times as compared to the fair iteration scenario. This brings up the question, does unfairness help all job combinations to interleave communication demands? To answer this question, we try out different DNN models. For example, let's take the popular image recognition model, VGG11. When I make the first VGG11 more aggressive, it seems that unfairness is not able to accelerate both the jobs. But when I take two DLRM models, DLRM is a recommendation model, on making the first DLRM model more aggressive, benefits both the DLRM models in accelerating their iteration times. This shows that there are some job combinations in which unfairness helps accelerate training for all the jobs in that combination.
We call such jobs as compatible job combinations. Here in this example, the second and fourth combinations are compatible, while the first and third are not compatible. So in order to utilize this benefit from unfairness, we need to understand which job combinations are compatible. But there are challenges here. Typically, DNN models last for a long duration. This means we have to check for interleaving for thousands of iterations for these jobs. Also, different jobs could have different iteration times, different communication durations. To solve this challenge, we introduce a novel geometric abstraction. Let's go back. Let's look at the communication pattern of one DNN model. What we see here is a periodic on-off pattern with a time period of 255 milliseconds. Let's leverage this periodicity. I'm going to draw a circle of perimeter 255 milliseconds and start rolling around the communication pattern around the circle. What we see here is all the compute phases of the 4 iteration falls on the first part of the circle, followed by all the communication phases of these 4 iterations. So this gives us a simple and compact representation to represent the entire communication pattern of a training job. By using a circle with one R representing the compute phase, followed by the second R representing the communication phase. Now let's use this geometric abstraction to find out which jobs are compatible. Let's take the 2 DLRM models which we saw earlier as compatible. We first construct the geometric abstractions for these 2 models. Now the question is, can these models interleave their communication pattern? To check this, we lay one circle on top of each other and start rotating it. When we rotate it, we see that the communication phases can potentially completely separate out. This shows that unfairness can actually slide the communication patterns of these 2 jobs and provide complete interleaving. Now let's take a different example. We take 2 VGG11 models, which we saw earlier as non-compatible. We again draw their geometric abstraction. And now when we try to roll the geometric abstractions, we see that no matter how much we rotate them, the communication phases do not separate out. This implies that no matter how much unfairness slides the communication demands, they cannot interleave their communication phases. Hence, our geometric abstraction shows that the second group is not compatible. This was easy to do when the jobs were same. What if different jobs end up sharing a network link? For example, job 1 could have a 40 millisecond of iteration time. Another job could have 60 milliseconds iteration time. This results in 2 circles of different perimeters, which no longer fit. To solve this problem, we take the least common multiple of the iteration times and create a unified circle. So here, the LCM of 40 and 60 is 120. So we now roll the communication pattern around a circle of perimeter 120. So we get 3 copies of iteration for job 1 around the circle. Similarly, for job 2, when we roll around a circle of perimeter 120, we get 2 copies of the iteration. Now both the circles have same perimeter, and now we can check for compatibility. So when we rotate the first circle by 30 degrees clockwise, we see that the communication phases completely separate out, showing that the 2 combinations, 2 jobs are compatible. This was easy to visualize when only we had 2 jobs sharing a link. What if multiple jobs share a link? To scale this approach, we translate the problem of compatibility into an optimization formulation. And the optimization formulation tries to find rotation angles to remove the overlap between the compute phases. So you might ask, what does this study imply? So we argue that there are 2 important next steps for ML clusters. First, ML schedulers should be aware of job compatibility and only place compatible jobs on network links. Second, even after placing compatible jobs, we need some way of controlling the unfairness so as to enable interleaving of communication phases. This can be done by multiple ways, like an unfair transfer protocol, or by using packet priorities, or by using flow scheduling. Our work demonstrates that fair congestion control protocols are not necessarily beneficial in ML clusters. Our geometric abstraction gives us a simple tool to identify which job combinations are compatible. And we argue that ML clusters should take job compatibility into account and only place compatible jobs on network links. Thank you so much, and I'm happy to take questions.
Okay, cool. So this was pretty cool. Thanks for the really nice talk. I have a question. So you're talking about compatibility and you've got the geometric abstraction and so forth. And I see how that tells me if they could be sort of interleaved in a nice way. But I thought the more interesting part of your talk was this notion of like, just doing the simple unfairness thing can actually cause that. So do you also have, some notion of how long it takes to converge to that, separated out form, or whether it will always converge to that separated out form if they are compatible?
That's a really great question. So in our experiments, what we saw is just adding some form of unfairness tells that it will eventually converge into this nice interleaving. But how fast they converge depends on how much unfairness it is. So if it's like 80-20, they'll take probably only two or three iterations. If it's say like 40-60, it might take 4 or 5 iterations to converge.
Cool, thanks.
Hi, Anup from CMU. I want to ask, like, do we really need to use unfairness from congestion control to cause these phases to interleave? Like, can't we just delay scheduling of jobs and then they'll naturally interleave, since we already know these iteration times, etc.? And another question is like, I'm assuming so these iteration times and communication phase times, like they would change as the load on the GPUs will change. So how often would you need to remake decisions of co-locations, or like, does that come into the picture?
Okay, that's a great question. So as I discussed earlier, like there could be different ways of achieving this unfairness that could lead into interleaving. As like there could be an unfair transport protocol, or as you mentioned, like flow scheduling could be a nice way to actually schedule different communication phases and interleave them. But
is it a networking problem or just job scheduling? So if you just schedule them at a different time, it'll work. Like, why does the network need to do anything?
The interesting aspect is like, once you place the job, say if you want to train BGG on certain servers, we need to schedule or like schedule the network traffic between the two servers. So it's not just placement, but also how you are sharing or how different jobs share the link network. And yeah, could you repeat the second question?
It's fine, we can talk.
Okay.
Yeah, let's go on to the next question. And then you can, maybe we'll follow up on that during the panel.
Yeah, shooting from UC San Diego. So I want to ask, like, so you talk about congestion, but like, what is your definition of congestion here? Like, because like what I'm seeing, the result you're showing is like, is actually the completion time is longer, but it doesn't necessarily trigger these like congestion. Is it like, do you see PFC or something that is like, I'm assuming RDMA, like, so is there any like congestion signal you're seeing like by them just uniformly sharing the link?
Great question. So in our experiment, we use DCQCN, which uses ACN marking and PFC. Here, the way I'm defining congestion is like when more than one job shares a network link and they both try to take up network bandwidth. That's how I'm vaguely defining as congestion. But yeah, as you mentioned, like there could be different congestion control protocols we can use.
I see. So it's more like crowdness instead of like explicit congestion control trigger, like PFC or like mark ECN trigger, like ECN mark trigger. Right? It's like you don't observe that in your experiment, right?
Yeah, we do observe. Like whenever we randomly place two jobs sharing a link, most of the time they end up having their communication phases together. That results in like congestion signals or PFC marks and ECN marks and PFC signals. Yeah.
I got one more.
Sarat Arslan from Stanford. Thank you very much. This geometric abstraction seems to be a very easy way to understand what's going on with the iterations. And I was wondering, so if I understood correctly, the main idea of that is that you are trying to somewhat prevent any overlap between the iterations so that you can give the entire bandwidth to one job in total. So I was wondering, in this non-compatible scenarios, could you still give the entire bandwidth to a particular job and let the other wait? And do you have any insights about like what kind of improvements could that bring to all of them, all of the jobs?
Oh, that's a really great question. Like currently I'm working on this. So as I mentioned here, we were relying on like complete compatibility. There could be a lot of cases when there's like partial compatibility, but still we can see that with proper alignment, the duration in which both of them compete can be reduced. In that case, either they can share network fairly, or we can give complete network to one job and start the other later. But yeah, I'm doing following work on these problems. Yeah. That's a great question.
So let's thank the speaker again. So we have one more speaker and then we'll have the panel session. Okay, so this is the last speaker of this session. And this is Marcelo. And he is a fourth-year PhD student from University of Colorado, Buffalo. His research is focused on building synergies among different packet processing environments, user space, kernel, programmable hardware. Today, Marcelo will be presenting Getting Back to What We Lost in the Era of High-Speed Software Packet Processing.
Yeah, thanks for the introduction. Yeah, I'm Marcelo from University of Colorado Boulder. And just a second. Yeah, and today we'll talk about our paper called Getting Back What Was Lost in the Era of High-Speed Software Packet Processing. So I start this talk by asking why we should care about Linux networking. And the answer is that we should care about it because it's widely used, and it's widely used because it has a rich ecosystem that can provide several features that we need in order to build network services. It has, for example, kernel functions to perform packet filtering and forwarding. It has management tools like IPRoute2 and iptables, and also it has powerful control plane software to provide, for example, routing protocols and IPsec. And this functionality is widely used on cloud and data centers today. For example, a common way to deploy scalable services on the cloud today is to use kernel-based technologies like, for example, Kubernetes and containers. So let's see how Linux networking is actually used in this context. So here in this slide, we can see a Kubernetes deployment that's composed by 3 pods. Those pods are basically a set of containers. And also in this deployment, we have one service. The service is basically used to expose the service provided by the containers to the outside world. So here to interconnect the pods, in this example, a network plugin, like for example, Calico, will interact with the Linux kernel to create virtual network interfaces, attach them to a bridge, it will configure routing, and also it may configure ACLs using iptables to protect the deployment. And also the service will be created by configuring either IPVS or iptables, again, inside the Linux kernel. So we just saw that Linux networking is rich, and also it allows providing almost all the features that we need in order to deploy a service on the cloud, right? Well, however, the problem is that Linux networking is proving to be too slow to provide the performance required by many cloud services. And this is especially true when we need to support network speeds on the magnitude of tens to hundreds of gigabits per second. As a result, to have better performance, several systems today, like for example, FastClick, they will rely on alternative processing pipelines, for example, using kernel bypass technologies like the PTK to implement several of those network services in user space. Another trend today is to implement those same network functions using technologies like eBPF and XDP, which will maintain processing inside the kernel. However, to gain performance, several systems that rely on this type of technology today, like for example, Cilium, Polycube, and Leaf, they will bypass the Linux network stack instead of explicitly leveraging it. And this leads to the unfortunate consequence that we lose the opportunity to leverage Linux rich ecosystem. And also we have to re-implement several of those functionalities either in user space or in eBPF. So in this work, we ask, can we just make Linux faster so that we can leverage its good features to build services rather than just bypassing it? So to make Linux faster, the first step is to understand why is it slow. And the answer is that it's slow because its networking is built to be general, and it needs to support different types of use cases and scenarios while handling complex corner cases. And to support this, Linux needs to rely on heavyweight data structures, and also it needs to rely on heavyweight protocol implementations. And this basically causes packets that go inside the Linux kernel to have a long critical processing path, which will prevent it to have high performance. So with these observations, there are two key insights that will lead to opportunities that we observe so that we can redesign Linux networking to make it faster. The first insight is that instead of mixing slow and fast path processing as Linux does today, we can break down Linux networking into a slow and fast path processing and instantiate a fast path on a specialized execution environment. The second insight is that most of the times, only a subset of Linux functionality is actually used on a given deployment. And this gives us the opportunity to avoid having a heavyweight data path, and instead we can tailor a minimal data path that will be based on what's currently configured. So with those opportunities in mind, now we ask, is this redesign realizable with technology that we have available today? So to do this redesign, what we need is a fast path execution environment that first is designed to be efficient. Second, it enables secure and dynamic code injection so that we can specialize data path based on what's currently configured, and we can deploy it on the fly. And the third thing that we need is that it enables interacting with Linux so that we can leverage its rich set of functionalities. And today, XDP and eBPF provide all those features. However, we still need to address three high-level challenges to allow us doing this redesign. The first one is to figure out how to break down Linux network processing into a slow and fast path. The second one is to ensure that this redesign will be transparent to the rest of the system. So we can, for example, continue using Linux APIs and management tools to configure it. And also we can continue using Linux protocol implementations to build our services. And the third challenge that we need to figure out is how to dynamically create the fast path that is light and will support only what's currently configured on Linux. So to address those challenges, we now introduce our system called TNA, which stands for Transparent Network Acceleration. First, let's talk about how we break down Linux network processing in TNA. So we do that by mapping complex functionalities, corner case processing, state management, and also other unsupported processing to a slow path that's provided by Linux, by the Linux kernel. The TNA fast path is composed by a library of fast path modules, which we call the TNA FPMs. And those FPMs are basically a set of pre-built and modular eBPF code that we build to support fast path processing for different network applications. Those modules, they are deployed at the XP layer. They can access kernel state using BPF helpers. They can send packets for corner case processing and also other unsupported processing to the slow path on the Linux kernel. And they also can be composed to build a lightweight data path. This breakdown allows us to have a fast path with minimal processing that will execute only a few simple tasks, but we'll be able to process the majority of the packets with higher performance. Next, we want to make sure that this redesign will be transparent to the rest of the Linux ecosystem. So as I mentioned, we can continue using Linux tools and APIs to configure it. And also we can continue using Linux protocol implementations to build our services. So here in this example, we can see that with TNA, an operator, a tool like Ansible or even Kubernetes can continue using Linux commands and APIs. For example, it can use BR control to create a bridge. We can continue using IP route to manipulate routes. and also use IP tables to add filtering rules. And you can see that by issuing these commands, the related kernel objects will be created inside the Linux kernel. And based on that configuration, TNA will dynamically create a fast path to support this configured functionality. And it will do that by continuously introspecting the Linux kernel using the netlink protocol. And after introspecting the Linux kernel, the TNA controller will find relationships among those retrieved kernel objects, and it will create a dependency graph representing the configured services. After that, the controller will dynamically compose a fast path, and it will do that by mapping each node or each of those nodes of the dependency graph into one or more fast path modules that will be stitched together to build the fast path. And finally, the controller will compile the fast path and deploy it at the XP layer. Now we show TNA's preliminary evaluation. Our first use case is to accelerate Linux Bridge. So in this evaluation, we compare TNA with Polycube, which is a standard, which is a state-of-the-art network function framework that also uses eBPF and XDP. So for doing this evaluation, we provision 3 physical machines. One generates packets, the other one receives, and the third machine will do layer 2 forwarding between the other 2 machines. So here we can see that currently TNA, depending on the number of CPUs allocated, it will be between 3.4 to 3.8 times faster than Linux. And also it's between 1.6 to 2 times faster than Polycube. So with this, I start concluding my talk. So we propose a redesign of the Linux network stack in order to make it faster. And we show that this is realizable with technology that's currently available on the Linux kernel. As feature work, we need to do a more comprehensive analysis of the Linux network stack so that we can decompose and accelerate more of its subsystems. And also we need to figure out how to ensure the correctness of the generated data plane. And also we need to explore debugging mechanisms considering this new architecture. Thank you. Actually,
hi, thanks for the talk. It's Kostis from Google. So first of all, I have 2 questions. The first one is do you synthesize the code? I mean, how do you generate the eBPF bytecode for each of the points in the chain?
Okay, so we are not directly generating bytecode. So we have some template files some pre-built template files with the source code. And we use a tool called Jinja tool in Python. So we can just manipulate the source code to add each of the processing functions that we need. So we are basically inlining a bunch of.
So it's like a fixed function pipeline, basically.
Yeah.
Okay.
Yeah,
makes sense.
yeah.
And the second question very quickly is like in some cases, it's not a chain of functions, right? So you need to make a choice and then you can select one of the 2 next functions, right? And how do we do that?
Yeah, so
when filtering, for example, or load balancing, I don't know, things like that.
Yeah, so if I understand the question, we may have different paths.
Yeah, exactly.
Yeah, so basically we will be just doing if and else clauses and send the packet. Continue the processing after the if.
So you choose a different next step in the pipeline based on on a clause.
Yeah.
Okay. Thank you. You can chat more.
Yeah.
Good work. Teacher from Cornell. I wonder what kind of functionality you implemented in the eBPF to put the TCP/IP some.
Yeah. No. So we are in this work. We are basically tackling. We started tackling different network subsystems one by one. So we started by tackling the bridge subsystem. So in the case of the bridge, what we have in XDP is just some basic processing functions to parse the packet, do rewrites, and also we build new kernel helpers to allow interacting with bridge code inside the Linux kernel. So to do destination MAC lookups inside the kernel and also get a response, rewrite the packet, rewrite the destination MAC and forward the packet. So it's very simple processing that we do on XDP, and we leave all state management and slow path processing, like for example, spanning tree processing we send to the kernel.
Cool. Very interesting.
And this is the last question for this session. The speakers, if you can maybe start to come up, sit down and go ahead and ask that question.
Hi, I'm Henry Burgely from Princeton University, and I want to apologize right off the bat if I'm incorrect in this assumption, but I think I had heard that Linux primarily processes packets on a single thread, and eBPF I know is a multi-thread. It utilizes all CPU cores when processing packets. I was wondering if you came across any like state synchronization problems with the fact that now packets don't necessarily go to the kernel in the order they were arrived at in the network.
Yes, so what we are doing, we are using RSS to distribute traffic between different CPUs. So we didn't see any synchronization problem because with our bridge implementation, we have all the infrastructure for locking the table and having safe access to the FDB table. And yeah, so I don't know if I understood your question correctly, but we are basically with RSS, you can get a key from your packet header and select and always send the packets from the same flow, for example, to be processed in the same CPU.
Okay, well that makes sense. Thank you.
So yeah.
Okay, let's thank the speaker one more time. So we'll have all the speakers come up. We'll have about 15 minutes for this panel session. People do need to get to flight, so let's try to stick on time and by about 4:15. So if you have questions, please, line up with both mics so we can go back and forth. Go ahead.
So this is Tal from UT Austin. So this is a question for the host congestion work. First, I really appreciate the observation there that the host can be congested, but this question is about, so in your presentation, you kind of assume that it is packets that gets delivered from the NIC to the host CPU DRAM, and presumably the transport actually runs at the CPU. So this scenario is kind of more or less tackled by, say, Swift, which includes kind of the delay here, and it kind of adjusts to some extent. It can adjust accordingly. But what's your take? As what comments do you have on, let's say, hardware offload, say RDMAs? It doesn't. So now this delay is kind of hidden from the congestion control plane.
Yeah, that's a really good question. So yeah, first of all, even with RDMA, we are going to see this host congestion problem. And one part of the answer is that I think just delay as a congestion signal, I don't think is the right signal to solve this congestion problem. Like I briefly alluded that, because delay as a signal will not give us the reason of individual like root cause of congestion, like whether is it the memory bandwidth causing the problem or the MME causing the problem. So you won't know how to ideally respond to that signal. And like you mentioned, Swift uses this delay for handling the CPU congestion. Now, if you use the same delay for handling host congestion as well, then it might run problems. Sorry, what was the second part of the question again?
So because now congestion, if you have hardware offload, congestion control actually runs below that.
Right. I mean, even if you transport on an offloaded, like on a smart NIC, for example, still like I'm imagining that if you still use like delay or NIC buffer occupancy as a congestion signal, you might still observe these fundamental issues, which I just pointed out. So I think it's not just like where your transport is run. It's like those two things, like what are your signals to the transport and how are you utilizing those signals, which I think we need to fundamentally rethink.
I see. So you think the future direction is more on how, what signal we should really use?
Yes.
And you think that where the transport sits is actually more or less immaterial?
Like today's transports, yeah. Because today's we have been just using the signals which have worked perfectly fine for the traditional in-network congestion. So I think we need to rethink the signals.
Thank you.
Thank you.
Hello, this is Jiaxing from UT Austin. I also have a question for the end-host congestion paper author. For example, in Intel machine, it has the DDIO feature, right? Allow the NIC to directly send the packet to the L3 cache. My first question is, I'm wondering how the DDIO would influence your observation. Did you still observe the end-host congestion and with the DDIO machine? And my second question is, what should be an interesting research problem for the end-host congestion is maybe we should think about develop isolation mechanism. For example, we should isolate the DDIO cache as well as the DRAM bandwidth between a memory contention application and a network stack. So maybe in this way we can make the network stack run faster and reduce the end-host congestion. And another thought is maybe we can redesign our network stack for the congestion control mechanism to allow all the network processing can fit the DDIO cache.
Yeah, I think these are all great set of points. So yeah, first you talked about DDIO. You're right. So we did observe problems even with DDIO on. So just to give a rough idea why, like there has been some like very recent works, like I think last year in SIGCOMM, there has been a paper which talked about the efficiency or efficacy of DDIO getting worse as you, for example, increase like more and more active number of flows in the network. So, and that's what exactly we saw as well. Like if your DDIO is very effective, you're right. You might see less memory contention, but in real world cases, when you're actually running lots of active connections, we see DDIO is like no longer super effective. Sorry, could you remind me the?
Yeah, my second actually is not question, it's a discussion topic.
Okay.
Like maybe we
The
need
isolation, right? Yeah. So yeah, you're spot on there. Like if you do isolation for network memory bandwidth separately, CPU memory bandwidth, there will be benefits. But again, I think it boils down to this whole resource imbalance, balance, and allocation question. Like, so for example, depending upon whether you do data copy or not, or you do zero copy, whether how effective DDIO is, the actual worst case memory bandwidth utilized by just your network traffic can already vary, like from say, from 1x to 2x or 4x. So how much memory bandwidth do you even allocate for network in the worst case? Even that is not a very trivial problem. And now suppose you allocated the worst case bandwidth. Now you're using zero copy, then you'll be wasting the remaining bandwidth. So I think there'll be those resource partitioning questions going on there. But yeah, if it was possible, then definitely it would help us.
Yeah, thank you for your answer.
Question at a time.
Yeah, sure. Hi, this is Jane from UT Austin. I have a clarification for Sudarshanan on the congestion control in ML cluster work. So I'm wondering if you're assuming the network to be oversubscribed, because I cannot think of a case when this congestion will occur in a full bisection bandwidth network. Because if your Tor links are fully utilized, then your upper links have enough bandwidth for both Tor links traffic.
Yeah, this is a great question. So definitely the system, like the situation becomes more worse if it's a like undersubscribed system. And I feel like even when there is like full bisection bandwidth, because of ECMP collisions, it is highly likely that multiple jobs end up sharing the same link for the traffic. And also like today's ML schedulers try to optimize number of workers per job and keep changing them as new jobs come in and jobs leave. So this creates a lot of fragmentation in the cluster. This makes the same job take up workers from different TORs and different places around in the data center. this increases the number of network links each job has to take.
Okay, thank you.
Just a quick follow-up. Say congestion in your title. That a little bit confusing. Really, the friendliness, that's the issue in trying to share the link.
Yeah, I guess like one way to think about it is like, can we have a distributed solution just based on congestion control to solve this approach? But the interesting aspect is like, we know almost everything about ML traffic. They are like periodic, on, off, and pretty deterministic. So we can have different solutions to solve the same, to get the same solution of interleaving, which could be like flow scheduling or priority queues or congestion control.
Hi, I'm Akshay from UC Berkeley. There were two talks about flow scheduling for machine learning training in this session, and I was wondering if you could comment on each other's approaches and what's sort of left after both of you bring your work to fruition.
Good question. So I think Sudarsana's approach is very elegant in a sense that it makes sense to like adjust the ring so that they match. But I guess one potential issue I see is that these network links are shared by multiple jobs at a time, and then I see a scalability issue in the sense that, if there are multiple jobs, then it's really hard to come up with a perfect match, and you might need to like tune some of the user parameters like batch size so they match. Sorry.
Okay, I'll first answer this question, I guess. That's a great point. Like all the the iteration time or the communication duration depends on what hyperparameters we use in an ML model. But also it's true that we kind of today have like a zoo of different types of models, each having like say small iteration times to large iteration times. And also we can play around with hyperparameters. So I still feel like I'm still trying to figure out like what is the percentage of compatibility across different DNN models available today. But I have a hunch that 50% of the model should be compatible, given that there's so much range of variety in these models. And as you pointed out, it's a great direction to look at. Like, can we play around with hyperparameters to make them more compatible? And I guess answering Akshay's question, my work focuses more on, I guess, like how does different jobs, when they share a link, how they interact. Ray's work is really interesting on like how do you flow schedule within a DNN model, which is across different servers, and how do you optimize that?
Hi, Divyanshu from UT Austin. Question for Sudarsana. So, do you have any insight on how many jobs roughly would share a link? Like in two jobs, I can imagine that this circle we can find some compatibility, but if it increases to let's say 3, 4, 5 or so on, it becomes increasingly hard. And with different iteration times for each of them, it becomes like even more complex to find like any compatibility. Is that the case, or do you have any insights on that?
Yeah, it's true. Like definitely it's easier to put two jobs and make them fit. But even when there are multiple jobs sharing a link, it could be possible that the communication phases fit completely. Or my current work focuses on how to enable like efficient network sharing when there is like partial compatibility. Say if one direction to look at it is some jobs might not need 100% network bandwidth, might not be able to use 100% network bandwidth. So can one job take say 30% network bandwidth, other takes 70%, and they still do perform well? Or like that's kind of like partial sharing of network. And the other point is like the compatibility could be partial. The communication phase might not completely fit in, but still we can have a best orientation which reduces the interaction between different communication phases.
And then, Sudarsana, I wanted to ask the earlier question about things at the network level versus. So let me try and ask it again. What happens if I just stagger the start time? I get the desynchronization as well?
If I'm understanding correctly, like we just stagger the start times of different jobs sharing a network link, and we are using unfairness, I guess.
Yeah,
But
because one of the things you achieve is that you desynchronize the computation of computation. And you did that at the network level.
Yeah.
So if I do it at the application level, that's the same effect.
yeah, definitely. Yeah. That's interesting about, like, I guess, ML traffic. Like when we know everything about when they compute and when they are going to communicate in future, we can align them nicely, either through the network level or through the application level, or the scheduler can tell when each job should roughly communicate.
Narek Galician, UC Berkeley. This is for the last speaker, for Marcelo. You motivated your talk by saying that we want to use Linux networking stack to keep this generality and all the tooling that Linux has. But my understanding is that once you use eBPF and this kind of fast path filters, you lose a lot of the tooling. For example, if you can do packet filtering with eBPF, but you're not going to be able to use IP tables anymore. First of all, is this true? And if so, can we still achieve the goal that you are trying to achieve with this?
Yeah, so the main idea is to build the specialized data path with the observation that we don't always need all the functionality that's inside the Linux kernel, right? So we are doing like a trade-off for the functionality and specialization in our data path. So if you just need a few simple stuff inside the Linux kernel, like bridging or routing, even if IP tables, it would be possible to have some acceleration. But if you need all the processing stack for some reason, you won't be able to have an acceleration on that. So.
And you get the honor of the last question for the panel.
Okay. Okay, that's another one for Salasana. It's not really a question, more like a comment. I think what you're doing is really collision avoidance by desynchronizing. And I believe it applies whenever you have any irregularity in requests and responses occurring, which would also apply to dash traffic, for example, video traffic, which occurs in bursts at regular intervals. Whenever these things collide, you can desynchronize them to do the same trick. So this was very interesting work.
Thank you so much. Yeah, I think any traffic pattern which has deterministic periodicity, we can leverage similar approaches to actually nicely place and make them avoid having congestion.
All right, so let's thank the speakers again.